at the end. So I might pass over to Scott then to begin the presentation. Thanks, Scott.
Thank you very much, Sonia. Can you hear me okay?
Yes, loud and clear.
Great, thanks. Good afternoon, everyone. Thanks very much for tuning in. And I'd like to acknowledge my long-time collaborators, Francois Delage and Christine Chung, and I'll be talking about some of the research we've done in the last couple of years. And I just really wanted to talk about two main topics. First of all, in case there are people out there that don't know as much as they would like to know about ENSO, just a brief introduction, what its impacts are, and particularly what it does to Australia in terms of rainfall, tropical cyclones and floods. And then I'd like to turn to the main part of the talk, which will be the impact of global warming on ENSO-driven rainfall variability. And we'll start off looking in the Pacific, which is the engine room for the El Niño-Southern Oscillation. And then we'll look around the world and in particular, what happens in Australia. And we'll look at what global warming will do to the magnitude of the variability, but also to the frequency with which El Nino causes major disruptions in the Pacific. So let's begin by a brief introduction to ENSO. And ENSO can be considered as a naturally occurring phenomenon which is centered in the tropical Pacific, and it consists of three phases. One is the neutral phase, one is a La Nina phase, and one is the El Nino phase. So it's a little bit like a rusty old swing where it can vacillate or swing between those various phases. So when not much is happening, we're in the neutral phase. And at the moment, we're in a neutral phase, but we're in an El Nino watch period. And there's an estimated 70% chance that we might end up with an El Nino later this year. And during El Ninos, you tend to get warming in the central or eastern tropical Pacific, as is indicated in this map here. So you get nice warm water over there, and you tend to get cooler water towards the west, including in the Coral Sea. And in the overlying atmosphere, you get very large changes. And one of those major changes are changes in precipitation. And that's depicted in this map here, where during an El Nino, you tend to get more rainfall near the dateline, and you tend to get less rainfall over Australia and to the north of Australia. And I'll be zooming in on that region where you tend to get larger rainfall. That's a key region for the dynamics of ENSO, but also for the impacts that ENSO has on countries right around the world. So in Australia, during La Nina periods, you tend to get greater rainfall, especially in the eastern part of the country, and during La Nina. And during El Nino, you tend to get lower rainfall and increased risk of drought. But there are a number of other effects that ENSO has, and let's have a look at a couple of those examples. So one is the impact on tropical cyclones, and we know that many parts of northern Australia are impacted by tropical cyclones, and that's nothing new. You can see here the aftermath of a tropical cyclone in 1893, where there was massive flooding through Brisbane and there was associated 23 deaths. And even earlier than that, there was a major tropical cyclone in Innisfail in 1918, and that destroyed nearly all of the houses were there, and it killed many, many people. And some work I've done with a long-standing colleague and friend of mine, Jeff Callaghan, former employee of the Bureau, used to be in charge of severe weather forecasting in Queensland. We wanted to document the variability and long-term trends in severe landfalling tropical cyclones that made landfall somewhere between or near Cairns, further south to northern New South Wales. And by severe, I mean categories 3, 4 and 5, where you can see clear visible evidence of structural damage from strong winds. And to cut a very long story short, Jeff looked at lots of different sources of information, including newspapers and Bureau of Meteorology reports, state reports, and we're able to come up with a time series of the number of landfalls that occurred from the early 1870s. And this is what's depicted in this time series up to near present. We're at the moment, we're updating that time series. But you can see that in many years, you don't get any landfalling severe tropical cyclones. Some years you get one, or many years you get one. Some years you get multiple landfalling cyclones in this part of the world. And it turns out that all of those 6 years in which we had multiple landfalls were all La Nina years. So clearly ENSO is playing a significant role there in modulating the frequency with which severe tropical cyclones make landfall over northeastern Australia. And another example where ENSO plays a big role in Australian climate is with major flooding. And again, some work I did with Jeff, we looked at major flooding along that band here in southeastern Australia. And again, you see lots of many floods that occurred since 1860. Some years you don't get any, many years you get 1, 2, and in one year there were 6 major floods. And it turns out that the frequency with which those floods occur are much greater during La Nina years than they are during El Nino years, as are the number of deaths associated with that major flooding. So that's a brief introduction. Now I'd like to get to the main part of the talk, which is to look at the impact of global warming on ENSO-driven rainfall variability, beginning in the Pacific. And we just saw that ENSO or El Nino tends to dry things out in Australia, and La Nina tends to make things wetter. Whereas if you look in the Central Eastern Pacific, it's the other way around. So in this particular location, Nauru, you can see that during El Nino years, the rainfall tends to go up, and during La Nina years, the rainfall tends to decline. And I've got this idealized schematic of that situation down the bottom. So you can see that there are long-term neutral conditions. So that's the rainfall, the long-term average amount of rainfall you get during neutral years. And then ENSO causes variability about those neutral conditions. So in this location, you tend to get more rainfall in El Nino and tend to get less rainfall during La Nina. And so if we want to know what's going to happen to rainfall during El Nino years and La Nina years and neutral years in the future in response to further global warming, then we have to consider 2 things. One is how the rainfall is going to change during neutral years. And the other thing is how the rainfall variability driven by ENSO is going to change. So in this simple schematic, and this is really a hypothesis for what might happen in that part of the world, the long-term rainfall you get during neutral years increases and the variability goes up. And of course, the situation may be very different in other parts of the world, and we'll look at a couple of examples. So this is the hypothesis for what might occur in the Central Eastern Pacific, that engine room for the El Niño-Southern Oscillation. So how do we test this hypothesis? We use mathematical representations of the climate system, and the world is fortunate to have many of these models now, including one that was developed jointly between CSIRO, the Bureau, and universities in Australia. There are many, many others around the world, and that's very useful to pinpoint or to try and pinpoint what might happen in the future. So what we can do is, for example, increase greenhouse gas concentrations, and we can look at what happens to the El Nino in the models and what happens to the rainfall variability in the models. And we can see whether or not there's a consensus among the models on what those changes might actually be in response to those increases in greenhouse gases. And to cut a long story short, what we found was that, lo and behold, the variability in rainfall in that part of the world, in the equatorial Pacific, does indeed increase. So in the plot, where there's a dashed oval, the rainfall variability is measured here or indicated here by the blue bar, the 20th century value, and the 21st century value is indicated by the red bar. So you can see that there's been an increase in the magnitude of the variability in rainfall in the equatorial Pacific. And the red star indicates that the overwhelming majority of climate models that we've analysed give an increase. So that the models at least tend to agree that the variability in that part of the world will increase, is projected to increase. And so this schematic, which we presented earlier, does seem to be what happens in that part of the world. So as that is the engine room for variability around the world, if it varies in the equatorial Pacific, that often leads to variability in other parts of the world, including Australia. So if the variability in the equatorial Pacific increases, then we might hypothesize that the impact that ENSO has around the world might also increase. So again, in order to test that, what we did was to look at rainfall variability, or rainfall averaged over the boxes represented here, 25 different boxes around the world. These are boxes that were used in the extremes report by the IPCC a few years back. And we wanted to know, is the impact of ENSO on rainfall in these boxes increased in response to that increased variability in the equatorial Pacific? And the answer to that is overwhelmingly yes. So that if you look out of 19 of the 25 regions presented, sorry, did someone just say something? No. So 19 of the 25 regions, there was actually an increase, and that's a result that's statistically significant at a very high level. That's for June, July, August. And you get a similar figure for December, January, February. So what does this mean for Australia and New Zealand? Because you noticed before that one of the boxes breaks Australia up into Northern Australia, and there's also a Southern Australia / New Zealand box. And what we find, in fact, is that a variability doesn't change very much in the models in that part of the world. So it's one of those exceptions to the general rule. However, in order to answer this question, what will rainfall be like in future El Nino and La Nina years, you not only need to consider, as I said before, the change in the variability, you also need to consider changes in what the rainfall will be like during neutral years. And if you look at the rainfall changes in the models during El Nino years, during winter, you find that rainfall tends to decline both in Northern Australia and the Southern Australia, New Zealand box. So that's indicated by the two bars on the right. So during the 20th century, the rainfall deviation during El Nino relative to neutral conditions is represented by this blue bar. So you get, as you know, you get less rainfall. And during the future El Nino years, the rainfall is even lower. And the same for, as I said, for North Australia and also for South Australia, New Zealand. But that decline, as we've seen, it doesn't come from a robust change in the magnitude of the variability. It comes from a robust change in the neutral rainfall, which can be very closely approximated by the long-term average rainfall. So in other words, there's a decline in the long-term average rainfall. And that results in El Nino years in the future that are drier than the El Nino years of the past. And a similar story is true for La Nina years. In the future, La Nina years won't be as wet as they used to be, according to the models, in either North Australia or in South Australia, New Zealand. So just to illustrate that point hopefully a little bit more clearly, this schematic shows a highly idealised situation for Southern Australia, New Zealand during winter for the 20th century. So you can see that during La Nina, you tend to get more rainfall. During El Nino, you tend to get less rainfall than the neutral value. But then when we go to the 21st century, as the greenhouse gases have increased and global warming has become even larger than it is now, there's been a decline in that neutral value, indicated by that red arrow, and the variability stays roughly the same. But you can see that the implications of this decline are that rainfall during El Nino is lower than it used to be, in 20th century El Ninos. Rainfall during neutral years is lower than it used to be in 20th century neutral years, and rainfall during La Nina years tends to be lower than rainfall received during La Nina years in the 20th century. So they all drop down. So you can see that relative to neutral conditions, El Ninos are projected to be much drier, and La Nina years are projected to be, rainfall during La Nina years is projected to be roughly the same as what it used to be during neutral years in the 20th century. So far what we've been doing is looking at changes in the magnitude of the variability that ENSO causes in rainfall. So now let's have a look at what might happen to the frequency with which rainfall disruptions might occur because of El Nino in the presence of global warming. And in particular, what I'd like to address is, has global warming already increased the risk of major disruption to rainfall patterns by the ENSO phenomenon? And in order to address this question, which was summarised in a recent paper, what we need is some objective measure of disruption to Pacific rainfall. And so what we did was to take a rainfall map for a given season and compare it for a particular year and a particular season to the long-term average rainfall for that season. And we made allowance for the fact that the long-term average rainfall patterns are changing because of climate change. So disruption here means disruption relative to whatever the latest mean state climate is. So it's a measure of the volatility, if you like. And if the difference between the rainfall pattern in a given year is very different to the long-term average, then we call that high disruption. And you can see in the plot to the left, what we've done is we've plotted a measure of disruption. So each circle represents the amount of disruption in every single season from 3 different sources. First of all, the observations, the red circles here. Also in the CMIP5 model, so that's the coupled climate models in the yellow. And also from the Australian Atmospheric GCM, forced with observed sea surface temperature. And you can see that they all tell roughly the same story, that the amount of disruption, and by the way, this is plotted against Nino 3.4 sea surface temperature anomalies. Nino 3 is a box which is in the Central Pacific. So when you're on this side, the positive side, that's the El Nino side. So you tend to get warmer water, as I mentioned near the beginning of the talk. And during La Nina years, the water in the Central Pacific tends to drop off. That's depicted here on the left-hand side of the plot. And you can see that the amount of disruption you get tends to increase as you move away from neutral conditions where there's not much of a sea surface temperature anomaly. And that's true in the observations, the CMIP5 models, and also in the atmospheric general circulation model when it's forced with observed sea surface temperatures. It's also interesting to note, as an aside, that the amount of disruption you get tends to be larger during El Nino years than it is during La Nina years. Now, in order to define major disruption, we chose what amounts to approximately a 1 in 10 year event under pre-industrial conditions. And that corresponds to this value here of 3 point something or other. And so whenever there's disruption above that threshold, we refer to that as major disruption. And so what we wanted to know is the frequency with which the disruption goes above this threshold increased in response to global warming. And we looked at the disruption under pre-industrial conditions, under historical conditions, and under future conditions for 3 different scenarios. 1 or 2 business as usual scenarios where greenhouse gases increase substantially above where they currently are. And another one where there are very large, widespread efforts made to reduce greenhouse gas emissions and restrict global warming to something like 2 degrees Celsius relative to pre-industrial. So the question is, does the frequency with which the disruption exceed this dotted line increase under any of those conditions? And this is a summary of the results. So it shows that the percentage change in the frequency of those major disruptions relative to pre-industrial values. So you can see that there's a tendency for the frequency of the disruptions to increase. And if we look at the late 21st century, this shows there's an increase here under RCP 8.5, which is the scenario with the highest increase in greenhouse gases. And by the way, that's consistent with some earlier work by Wenju Chai and his group. So they highlighted this result here, that under that scenario, you get a marked increase in the frequency of disruptions in the Pacific. But it's also true under RCP 4.5, which also exhibits large increases in greenhouse gases, but not quite as large, or not as large as RCP 4.5. And then in the last one, RCP 2.6, that corresponds to a strong mitigation scenario where greenhouse gas emissions are markedly and sustainably reduced. But unfortunately, you can see that the models indicate that the frequency of those major disruptions increases in all of those scenarios, including the scenarios where there is strong mitigation action. So that's for the late 21st century. When does this increase in disruption actually begin? Well, it's also clear by the early 21st century. And in fact, if you look in the late 20th century, there's already been something like a 35% increase relative to pre-industrial values. And the filled circles mean that there's general agreement among the models that there has been an increase. So this indicates that we don't need to wait until the end of the 21st century to see this effect. In fact, the increase in the risk of this disruption seems to have been already increased by the end of the 20th century. So that suggests that, for example, the 2 main El Nino events that occurred in the late 20th century, the 1982-83 and the 1997-98, they were natural events, but their impacts on rainfall may have been exacerbated by increases in greenhouse gases that had already occurred to that point in time from the beginning of the Industrial Revolution. So in conclusion then, we've seen that ENSO is a naturally occurring phenomenon that's centred in the Pacific, but it has global impacts. And we've seen that ENSO has a profound impact on Australia, and that includes rainfall, and it also modulates the frequency of flooding and associated death tolls, as well as the frequency with which severe tropical cyclones make landfall over northeastern Australia. And we also saw that there are projected increases in, generally speaking, in ENSO-driven precipitation variability, both within the tropical Pacific but well beyond the tropical Pacific. And we also saw in the last study I showed that the frequency of major disruption to Pacific rainfall increases even if strong mitigation action is implemented. And also that the frequency of that major disruption to Pacific rainfall because of global warming may have already increased by the end of the 20th century. And for Australia, we didn't see any robust projected changes in the ENSO-driven variability in precipitation, averaged over that those boxes that I talked about. However, we did see mean state changes or changes in the rainfall during the neutral years, and that resulted in, for example, El Nino years being drier in the 21st century than they were during the 20th century. And one important caveat to note is that the large majority of what I showed today is based on the output of climate models, and climate models are a magnificent tool. These are, in my view, one of the great achievements of humanity, the ability to simulate using mathematics and physics the climate system and its variability and its response to things like increases in greenhouse gases. But it should be noted that they're certainly not perfect. And in fact, we do know that there are deficiencies in the ability of the models to simulate long-term average climate in the Pacific, aspects of ENSO variability, and also observed multi-decadal changes in the Pacific Ocean. So clearly, we need to, so therefore there is a caveat on what the results that those models yield. And in the future, what we hope to do is to look more closely at what happens over Australia. We also are planning to conduct similar studies, but using the next generation of climate models as they emerge, and they're hopefully going to be improved and hopefully have better simulations of the Pacific climate and ENSO, for example. And we're also working with Daewoo Corono and others at CSIRO to look at what the implications of this sort of these results are for drought in Australia and possibly beyond. But thank you very much for listening.
Fantastic. Thanks, Scott. Really fantastic overview of what's going on in this space in our community. So thanks again. You covered a lot of information, so that's great. We have a few questions coming in, which I'll read through now, but just also a reminder that we've got plenty of time for questions. So if there's anything you're a little unsure of or you want Scott to delve a little deeper into any part of his talk, do just pop your question or comment into the chat bar that's available in the Zoom platform. So we'll start at the top, Scott, of the questions, which I have coming in from Ian, who asks, how do we interpret the greater disruption shown by the AGCM relative to the CMIC 5 ensemble?
I'll just go back to the slide that Ian's referring to. Oops. I'm not sure you could conclude that. So Ian's saying that there could be a difference between the amount of disruption evident in the CMIP 5 models relative to the observations, but I'm not sure we could necessarily conclude that. I'm not sure if the difference between the red and the yellow circles is statistically robust, because there's only one 50-year period in the observations, whereas CMIP 5 we've got multiple models and multiple eras. So, but having said that, I wouldn't be surprised if there were some differences, because the sea surface temperature variability that's applied to the atmospheric general circulation model is from the observations, and that's a little bit different. That has a slightly different statistical character to the sea surface temperature variability that's evident in the CMEP5 models.
Okay, we'll move on to the next one, which I think might have come from David Caroli, our hub leader. He says, Scott, you mentioned El Nino, but not the differences between the Eastern Pacific and Central Pacific El Nino. Yeah, is there a difference in the climate change impacts on the two different types of El Nino?
So the studies I talked about today were focused on the leading pattern of ENSO, which is it's a sort of a hybrid of the two. But we did have a previous study in Nature in 2013, and one thing we looked at was how global warming might affect the frequency of those Central Pacific El Ninos using the CMEP5 models. And we found that the models don't do a very good job of simulating the spatial structure of the Central Pacific El Ninos. But nevertheless, the four best models indicated that there would be an increase in the frequency of those Central Pacific El Nino events. And that's as far as we've looked into that issue.
Okay. The next question comes from Will Howard from the Department of the Environment and Energy. He asks, how much rainfall variability in the extratropics is now driven by ENSO?
I'd have to go away. I'd have to go away and dig the numbers up for that one.
Okay,
so I don't really have that at the top of my head.
Perhaps we can take that on notice.
I'll take that on notice, and I'll send you something, Will. And it'll obviously depend very much on where actually you are in the mid-latitudes.
We'll also ask another question. He asks, in the CMIC projections, how are El Nino La Nina years distinguished from the neutral sea surface temperatures anomalies in Nino 3.4 as in the observations?
Right. Yeah, so how do you actually define it? How do we actually define El Nino La Nina, given that you've got a background state that's changing? And that's one of the challenges of doing this research. So that's one thing we thought a lot about. And in the end, what we did was to use a spectral filter, and that enables you to remove the very low frequency changes, which are dominated by the anthropogenic warming. And then we then define the El Nino and La Nina years in terms of the remaining sea surface temperature variability in the equatorial Pacific. And I think that's one way of doing it, and that's the way we've done it. But I think there are other ways of achieving roughly the same thing. But the challenge is always the same. You want to try and remove the anthropogenic influence on the slowly, multi-decadally changing sea surface temperatures, or whatever it is you're using to define your ENSO event, and leave the El Nino part left. We tried a few different ways, and it didn't have a major impact on the results. It didn't change any of the major conclusions, let's put it that way.
Okay, well, we don't have any more questions that have come in. We've still got a few minutes, so if anyone does have another question for Scott, do just write it in the chat box there. I guess in the meantime, I'll just give a little bit of a plug for our next Earth Systems and Climate Change Science webinar, which will be next month. We're hoping for around about the 27th, Tuesday the 27th of November. Just a little unsure at this moment because the presenter, Professor Nathan Bindoff, is currently on the Southern Ocean in a research vessel. But that webinar will be provided by Nathan Bindoff from the University of Tasmania, and he'll be giving a bit of an overview of the processes and the findings of the upcoming Intergovernmental Panel on Climate Change Special Report on Oceans and the Cryosphere. So that'll be really fantastic, and the usual sort of email reminder will go out close to the date about that. Since we don't have any other questions that have come through, and Scott, Ian and Will both say thank you very much for your responses to their questions, we might wrap up early today, so you've all got a bit of an early mark. I'd like to thank Scott Power.
Oh, sorry, Sonia, could I, even though we've got a little bit of time, just
sure.
make one further point. So you often hear that people say, oh, there's high uncertainty about what global warming will do to El Nino or to ENSO. And there's still, we don't have high confidence in what our projections of ENSO-driven variability are. But I think the research that I've presented today, and also some other related research by other colleagues around the world, indicates that we have, or the models tend to agree on how global warming will influence ENSO-driven precipitation variability. Despite the fact that there's higher uncertainty in what ENSO-driven sea surface temperature variability will look like. So I don't think it's correct to say that there's low confidence in all aspects of how ENSO variability might change in the future. I think we have greater confidence in how ENSO-driven precipitation variability might change relative to how ENSO-driven sea surface temperature variability might change.
All right, fantastic. Well, in that case, I'll thank you, Scott, again, from the Bureau of Meteorology for giving the Earth Systems and Climate Change Science webinar. And thank everyone for attending. And if you have any other questions or something you're thinking about ENSO and rainfall that you want, please do get in contact with either Scott or myself. I think, Scott, on the last slide of your presentation, there's your email contacts, or else you can contact the Hub and we can answer any questions you have about that. So, yep, there's Scott's email address at the bottom. Please don't hesitate to contact him if you have any other questions. So once again, thanks from us, and we hope to see you at the next science webinar. Thank you. Bye.
Thanks very much, Sonia.